taking derivatives of functions that are not solved for y. And so here's basically what we have to remember for this. This is the key. There's two things. Those blanks are really long. They don't need to be that long. Okay, turn to your neighbor and fill in the blank. What are the derivatives of x and y? If you want to look back to the warm-up, okay, what is the derivative of x? 1. What is the derivative of y? dy dx. Or we can write it as y prime. So that's what we were just doing in the warm-up, right? Anytime we were actually taking the derivative of x, we got 1. But when we're taking the derivative of both sides here whenever we do this. So the derivative of the left side is dy dx, that's the derivative of y. The derivative of the right side is whatever this ends up being. But anytime we do the derivative of x, it's just 1. So that's what we need to remember for implicit differentiation. Whoa, hello, where'd it go? So this is going to mean we're going to use the chain rule. When taking the derivative of y. Of any kind of y expression. Let's say that. Of any expression with y. So this is the types of questions that we're going to see. Our function here is not solved for y. It's just got y mixed in there with x. And we need to find the derivative of this. So take a minute right now with your partner. Discuss. What do we think the derivative looks like? What do we think the process is? Or maybe you remember some from last year, but maybe you don't. And don't worry, I will show you how to do it in just a sec, but just go ahead and
We're just taking power.
Oh yeah. So like you have the
Negative minus 2 divided by Wait, hold on. Why is it negative 2 You don't know. I learned this yesterday. I can remember how to do this.
Okay, let's talk about it. So here's how it works. we just start, let's just look and take the derivative of all these things. So is there any product rule in here that you guys see? No. Any quotient rule? No, we just have separate terms added and subtracted. So this is technically our sum and difference rule. We just go term by term. So if I see y squared, what rule would I want to use to take the derivative of y squared? Power rule. So this would be 2y, now to the first power, times the derivative of y, which is dy dx. So that's how we're using chain rule. We do the power rule first for the squared part of it, and then we actually have to do the derivative of the inside, quote unquote, which is y. So times the derivative of y, which is dy dx. So we do the same thing. If this was like 2x minus 2x, what would our derivative be? Just minus 2, because the derivative of x is 1. But this is going to be minus 2 dy dx. Yes. And then we would do plus 3, and then equals 2x. So our process for x and y is the same. The only difference is whenever our expression has y, we multiply by dy dx, because that's, like, y is actually a whole function. And so we need to multiply by that dy dx. Okay, this is step 1. We have not found dy dx yet. What we need is dy dx equals. Turn to your neighbor, how are we going to do that?
Subtract the 3 and then take the whatever the plot is called out. Take dy dx out and then divide by x minus 2. Man, Caleb, you're amazing at this. How did you get that? Yeah, totally.
Okay.
Totally due to my.
That's right. It's a natural. So we need to solve for dy dx, right? How are we going to do that?
Subtract 3 from both sides.
So we're going to subtract that 3 so that we only have dy dx on this side. Then we
take out the dy dx.
Yes. Factor out dy dx. And then
Divide by 2y minus 2.
Okay, so there's our derivative. What this reminds me of, this process, it reminds me of last year in pre-calc when you guys were solving stuff like this. Do you remember how to solve those equations there? What do we have to do? Can't set the bases equal with 2 and 3. If it was 2 and 4, we could. 2 and 16, we could. Different bases, Liana? Yes, we could take the log 3 of each side. We could take log 2 of each side. We could also take, actually log base anything of both sides. Just it kind of depends on how our answer is going to look. Yeah. If we take the log base 3 of both sides, it cancels out the right side, but we get log 3 of 2 to the x plus 3. Then we can move this power down. Then we can distribute. Then we can get all the x's to one side. Then we can factor out x. It's kind of a similar process. Here we're moving all the terms that have dy dx to one side so that we can factor it out and divide. Last year in pre-calc, you guys solved problems like this where you got all the x's to one side so that you could factor out x and divide. If you don't remember it, go back to your notes from last year. Just making a connection here. Okay, we're going to come back to this one later and take the second derivative of it. Second derivative. Actually, no, we're going to do it right now. Let's do it right now. You guys go ahead and try first. Take the second derivative. Or take the derivative of this. What rule would you use? What do you think that would look like? Talk about it. Bless you. Okay, this is how you write the second derivative, by the way. D squared y over dx squared. Instead of saying that, though, we just say the second derivative. Okay, so what rule do we need to use to take the derivative of this expression? Quotient rule. So we start with the derivative of the top, which is 2 times the bottom, 2y minus 2. Okay, and then what comes next? Minus the derivative of the bottom. What's the derivative of the bottom?
2 dy dx.
2 dy dx. Because the derivative of y is dy dx. So when we take the derivative of 2y minus 2, it's 2 dy dx. Okay. Derivative of the bottom times the top over bottom squared. Okay. Now, the only thing is, thank you. We're not done because we still have this. I don't know why it does that. We still have this dy dx in there. So what we actually need to do is we need to substitute in dy dx, the actual expression in for dy dx. Now we don't need to simplify this. But we can't leave dy dx in there for our second derivative. So.
Are we gonna have to simplify?
Usually no. Sometimes, occasionally yes. But what's more likely is that you have to evaluate this at a given point. But less likely that we have to simplify this. Okay. Let's do another example. This one's going to have a lot of steps to it, but we're just going to say, we're going to start with this. Given evaluate. Okay, so we'll go through this step by step as a class here, but turn to your neighbor. What do you think the first step is?
Just 2x and negative x squared.
Well, no, because I'm subtracting it. I'm making it easier for myself.
I'll just do that later.
Plus.
Okay, what do you think the first step is? What's our first step going to be? What do we do first? What are we doing first? Like what are we doing? Find what? The derivative. Find the first derivative. Yes, find dy dx. That's our first step. Okay, you guys do that, then we'll check. Hmm? Yeah, I had to do the product rule.
Wait, isn't this equal to 0?
Yeah.
Yes, it is. Thank you. So now we have to solve for dy dx.
What's this? What?
Okay. Did you guys get this for dy dx?
Yes.
Okay, so I move the 2x and y over to the other side by subtracting them. Then I'm factoring out the dy dx from both. Then I'm dividing by what's left over. Okay. What's our second step going to be? What's our second step going to be?
Find the second derivative.
Find the second derivative. Yep. But don't substitute dy dx. And I'll tell you why once we get there. Okay, did you guys get this for the second derivative? Before we substitute. So notice when I do the derivative of the top, negative 2x minus y, it's negative 2 minus dy dx. That's here, it's got to be in parentheses, times the bottom, minus, then there's the top expression. The derivative of the bottom is 1 plus 2 dy dx. Okay, we're not going to substitute in dy dx just yet. Because what are we trying to do in this problem? What the problem tell us to do?
Evaluate at 1, 0.
Evaluate this at 1, 0. Yeah, this is what we're looking for. So, what we are going to do instead of substituting in for dy dx is we're going to evaluate dy dx at 1, 0. This is how you write that, by the way. Showing that you're plugging in that point for dy dx. What do we get when we plug in 1, 0 to dy dx?
0.
We get negative 2. Right? 1, 0, 1, 0. So negative 2 times 1 over 1. So now instead of substituting the whole expression in for dy dx right here, we're going to substitute in negative 2 at that point. So we're going to write that like this. And now we're just going to plug in all of our values.
Or would the second term be 0?
The second term?
Like the x plus 2y.
X plus 2y equals 1.
So why'd you cancel it out?
This equals 1. Equals 1. I canceled this out because in the first part I got -2 minus -2, which is 0. So it zeroed out the whole first term there. Yeah. Okay. Questions on this? Once we're here plugging in numbers, it's just plugging in numbers. But what I wanted to show you guys was instead of plugging in the expression for dy dx, we're plugging in the number that we evaluated for dy dx. That's usually what we're going to have to do with the second derivative, is evaluate it at a point. Okay. Do one more example here. I'm trying to find a good one.
It was just the XY.
Yeah, we'll do this here. Okay. It tells us the concavity. We'll get to that. Okay, pause for a second. We know our tangent line is going to be y minus y1 equals m times x minus x1. We know where we're going to get m from. Where do we get m from? The derivative, right? We plug our point into the derivative. Okay. X1 and y1. What's x1? Okay, what's y1? Turn to your neighbor. Figure it out. What point does this go through?
This is actually looking fun.
Are you guys getting this? This is how you show that you're plugging it into that curve, by the way. Because we can't say like y of 1 because we're not plugging it into, well, we are plugging it into x, but the curve's not called y. So we just call it the curve. So what does y equal? Y does equal 0. What else does y equal? Square root of what? Yeah. What else does y equal? Yes. Okay. We have 3 points. So if we set those separate factors equal to 0, and we solve this, 2y squared equals 1, divide by 2, take the square root, that's how we get those right there. So there's 3 tangent lines at x equals 1. Which one do we want? Which one's the easiest? Y equals 0. But that's just only because we're choosing it right now. Let's do this one. Sometimes you'll be asked to find all 3. Or to find 2. But just to visualize this curve, I'm going to graph it on Desmos here. 2x squared. Okay. Here's our curve. So we see here at x equals 1, we have 1, 2, 3 tangent lines right there. So we're doing this one at the point 1, 0, but there's 2 more. This curve's crazy, eh? It's not a function. Fails the vertical line test a whole bunch, but that's what we're taking the derivative of. Okay, so let's go back and change this to say find the equation of the tangent line to this curve at the point 1, 0. Okay, now you guys do that. And I'll go first. Okay, so we know we're going through the point 1, 0. So I know my tangent line is going to look like this. We just need to find the slope, right? How do we find the slope? Derivative. So what's my derivative of 4x? 4 plus
4xy.
4x plus 2x squared dy dx. Nice. Minus 12y squared dy dx equals 0. Okay. When we solve this for dy dx, what do we get?
Negative 4 minus 4xy over 2x squared minus 12y squared.
Okay. And you can start to do that quickly if you say like, okay, I'm going to subtract both of these and then factor out dy dx, and so I'm going to be dividing by this 2x squared minus 12y squared. You can see it in there before you actually do all those steps, so it can help shortcut the process. Okay, if I'm feeling fancy here, I could simplify like a 2 from these. if I want to make it easier to plug a point in. I don't have to though. But when we plug in the point 1, 0, so again, we write that like this. dy dx 1, 0 in parentheses, like a little line. That shows that we're evaluating it at that point. That's just what that means. What do we get for dy dx at that value? -2. Okay. There we go. There's our tangent line. So, just for funsies, y equals -2 x minus 1. Ta-da! There it is. There's one of them. The blue one there. Okay. So